When we think about temperature effects on the rate of a reaction, it may be helpful to analyze the energetics of a reaction first. Let's see why we need a certain amount of energy to actually make chemicals react together. And this is an important diagram that we're going to talk about. It's called a reaction coordinate diagram. And we're going to see that the x-axis here is really just not really very defined. We're not really dealing with numbers here. It's reaction progress. So start of the reaction to end of the reaction. That's all we're looking at. So it's not really something we really care about. The y-axis, though, we do care about. And that's going to be energy. And we're talking about the energy of your chemical substance. So as it starts as the reactants, as it gets changed to become a product, how are the energetics of your compound changing? And so we're going to see that for a given reaction, we might start off at a certain energy. We see that in order to break bonds, remember that breaking bonds always takes energy. So if in order for reactions to happen, bonds need to rearrange, right? Bonds are breaking, new bonds are forming. But because bonds are always breaking in reactions, we're going to always have an uptick in energy as we go through this. So our energy goes up of our system. And depending on the type of reaction, let's say this is an exothermic process. An exothermic process will end up having an energy that is lower than it was to begin with. And we have some important metrics we can make about this. What we already know, the difference between the products and the reactants, well, that was just delta H, right? We're going to see this is an exothermic reaction, so delta H will be negative. We have lost energy as a result of this reaction. In this case, delta H is negative, so this is an exothermic reaction. We'll look at an endothermic reaction next. But what about the difference in energy from the beginning to that hump up there, the very top of it? Well, we have a name for that too. It is called EA. And EA is what's called activation energy. And this is the minimum energy a particular molecule needs to have in order for it to do this particular reaction. And it's going to be specific for every reaction. So we can say it's kind of a constant for a particular reaction, but we'll see that, of course, we saw previously how at different temperatures, different numbers of molecules have sufficient energy and all that. So it's kind of our threshold there. And this very peak, by the way, is what's called the transition state. It is basically where we are breaking our old bonds and forming our new bonds at once, that kind of in-between stage. Sometimes you'll see this as a kind of, it's not quite a not equal sign. They call this a double dagger, but a transition state is abbreviated with this symbol. So you might see something like, for example, A going to A transition state to B or something like that. You might see something like this. You may see it as A with a star on it. It's really when you're looking at reaction mechanisms that you focus on the transition state. So that's what we're looking at here. So with these numbers, we've already looked at delta H, right? We saw that that's the enthalpy for the reaction, right? The change in energy that's happening. So we've lost energy. This is an exothermic reaction, so our delta H is negative. Notice that our energy is lower than where it started with at the end of the reaction. So we have a negative delta H. Of course, reactions can always go backwards, as something we'll see with equilibrium. But in order to do so, in order to go forward, the components only needed to reach the activation energy. Once they reach the activation energy, they can go downhill from there. We have to just push them up the hill, up till that point, and then they can go down. But if we're starting at the bottom, That's a lot more energy. We now have to beat both delta H and the activation energy. So to go all the way up is unlikely. So it's unlikely for us to go all the way back up again. So we're going to not even consider that. But really, to do that, we have not only the activation energy, but now we have delta H as well to go backwards. So not very likely to happen for an exothermic reaction. If we take a look at an endothermic reaction, it looks similar. I'm going to actually start this one a little bit lower. This would be an endothermic reaction. That symbol is xi, the Greek letter that means reaction progress, but we'll put that. Not really something we'll ever have to worry about. We've got our energy here. So just like before, we have our activation energy. Activation energy is always determined between our reactants and the transition state. And so it just depends which way we're looking at the reaction. Remember we saw before that exothermic reactions, the reverse of those would be endothermic reactions, whatever that reaction happens to be. So the activation energy is always the hump that you're looking at, whichever direction it is. And in this case, we have our delta H as well. And in this case, delta H is greater than 0. We've gone up in energy, so this is going to be an endothermic reaction. The other marks are the same, so we have the transition state and all, and everything else would be the same. So with that, now that we've seen this idea of activation energy, we can actually now put it into practice. So way back when, Arrhenius, a mathematician, or I guess he was a chemist, derived an equation to describe the activation energy and essentially the amount of molecules that would have it at a given temperature. And the equation that's derived from this is the following. It's an exponential function where we relate the rate constant with another constant. This constant A is not dependent on temperature. It's essentially a way of kind of going from just general reactions to our specific reaction. It's going to be something special for all reactions. They will have their own A constant. But we don't need to really worry about that. Of course, EA, we have the activation energy. R, of course, is our gas constant, but typically we use the joule one because activation energies are given in joules or kilojoules. Notice we have joules per mole Kelvin again is our units. And then we have our temperature in Kelvin. And so this equation will allow us to calculate the rate constant for any reaction if we know its activation energy. Or if we know the rate constant, we can determine the activation energy based on doing some comparisons. If we go ahead and mess with this equation and take the natural log of both sides, which we can do, remember that if you have a product within a natural log, you can separate that as addition or subtraction. So we have A times E, so we can go ahead and split those apart. ln of A becomes ln A. ln of E to the whatever just becomes the whatever. So we will have this component here, negative EA over RT. And if we go ahead and do some tweaking around, we can go ahead and rearrange this equation. Plus ln A. And hopefully we see that we have another slope-intercept line here. The natural log of your rate constant if we consider the activation energy to be the slope, 1 over RT is our x. Although really E over R is going to be our slope. 1 over T will be our x. So we're going to see that y is this thing. M would be negative EA over R. And then x is 1 over T. So that means we're going to be graphing this with respect to 1 over the temperature. And then we just have our intercept, which will be the ln of A. So that's just B. So graphically, what this might look like. So if we're plotting 1 over the temperature, we're expecting the reaction rate to go down, right? This will be our natural log of K versus 1 over the temperature. We're looking at this typically to go down, and our slope is negative EA over R. And so R, of course, is a constant. We could move that in with the temperature term, or we could leave it with the slope term. It doesn't quite matter. And so in either case, that's what we're looking at here. So we can plot various rate constants, which are experimentally determined, for the same reaction at different temperatures. Once we do that, we can figure out the activation energy for that reaction. So all we really need is 2 points, right, to form a line. Of course, you'd do more. You'd do the same reaction at maybe 4 different temperatures. You would end up with 4 points. Now you've got a pretty good line, hopefully, and just take the slope of that line, and that'll tell you the activation energy of your reaction. And so that's how we can determine this experimentally. And the last thing is, if we want to take that idea of taking multiple measurements at the same time, we can throw it all together. We can combine that if we have ln of K1 equals negative EA over RT1 plus ln A, right? A is just a constant. We're going to see we can get rid of that. And if we have the same thing at a second temperature, if we combine these 2 reactions, we get the following. We're just going to compare the 2 of them. And in doing so, we get EA over R times 1 over T2 minus 1 over T1. And this way, we can make it all positive by switching the 1 and the 2 there. So we can compare the rates of the reactions at the temperatures. So thankfully for this, we can figure out the EA from a graph, right? Or we can just use it as a constant. But we can get the we can actually now compare things. We can say, okay, well, I know the rate constants are here and here, and I can figure out what's going to happen with the temperature as I do this. In our next video, we'll actually take a look at using this equation to see how to actually use this information.